All right, we'll go ahead and get into the next section of notes for this unit here. So this is going to be 9.2, and we are talking about the Pythagorean theorem again. Date that we are doing this is the 26th, if you'd like to add that as well. Okay, so like I mentioned, we're doing this again. We've seen the Pythagorean theorem before, but now we're going to relate this to more ideas that we're going to use later on in this unit with trigonometry, and we're just going to go in general a little bit deeper with the Pythagorean theorem than we saw the last time. Okay, so that's our objective for today. So as a reminder here, if we're looking at the Pythagorean theorem, what is that theorem? Okay, Pythagorean theorem, it helps us determine values, specifically side lengths in right triangles. And the Pythagorean theorem is this. I'll just go ahead and write it out. We'll just say a squared plus b squared equals c squared, right? And you can go ahead and underline that, put a circle around it, box around it, whatever. Okay, but make sure this stands out. Okay, you've seen this before. This helps us solve for different side lengths. And again, if I'm thinking about what this is going to look like here, this only works with right triangles. So I'll go ahead and draw a right triangle here, roughly. Okay. Remember, we have different parts of a right triangle. The two sides that make up the right angle are what we call the legs. So each of those is a separate leg. And then remember, we have a name for the longest side, the side that's always across from the 90-degree angle. That is what we call the hypotenuse. Okay, that is what we call the hypotenuse. So I have these types of sides here, and this is helpful because if I have two of them, I can use the Pythagorean theorem to find the third. So as a reminder, what all these letters mean, A, B, and C here, A is always going to be or represent our shortest leg. B always represents the longest leg. And remember, that's longest leg, not necessarily longest side. And then C is always going to be the hypotenuse. And that one will always be the longest side. That will be the one across from the 90-degree angle. Okay, so we can use this. Like I said, this should be a review. You should have seen this in this class and then some other math classes as well. So making sure we understand and remember how to use this to solve for different lengths here. Okay, so example 1 here, if you'd like to, you can go ahead and pause your video and sketch these here. But I want to use the Pythagorean theorem to find x. Okay, and again, I've mentioned this in the past. If you need to, I would recommend labeling your sides first between A, B, and C before you plug them into your equation. Just a good little step there to remind me where they're going to go. So notice I have the two legs here. I see 6 is the shortest leg, so I'm going to label that A. 15 is the longest leg, so I'm going to go ahead and label that B. And then x we know is the hypotenuse, which is C. So just a little habit that we can get into to help us here. And now that I have this, I can go ahead and just plug this into my equation. So again, it's a squared plus b squared. So 6 squared plus 15 squared equals x squared. Okay, using this to solve for different lengths. Now we can go ahead and simplify this here. So 6 squared. Remember, squaring is just multiplying a number by itself. So 6 times 6 is 36 plus 15 squared. If we didn't know this, we could just type this into our calculator. But that is 225, and then equals x squared. And then add these together here. So I have 36 plus 225. That should give me 261, I believe, equals x squared here. 35, yep, okay. So we have 261, and then remember, we don't want x squared, we want x. So that last step that we mentioned is we need to do the opposite of squaring a term. We need to square root both sides. So when I square root the right side, the squared term and the square root cancel each other out, which is what I'm looking for here. And then on the left side, I have this here. We have square root of 261. 261. And usually, we talked about this when we were going through this in first semester, we said, we'll type this into our calculator. If it comes out to be a whole number, we'll write that. If it doesn't come out to be a whole number, we'll leave it as is. Okay, but this is why we went through that lesson last time with simplifying radicals, because if I don't know if it doesn't come out to be a decimal, or if it comes out to be a decimal, I need to simplify this radical now, because I know I can simplify it more than just leaving it this way. Okay, so as a reminder, to simplify radicals, we need to look at this number and try to figure out if there's any perfect squares that go into this here, and there actually is one. Okay, one of the smaller ones that we have. This would be a multiple of 9. I'll go ahead and type this in my calculator, just double check. Okay, this does come out to be a multiple of 9, this is the same thing as 9 times 29. So remember we split them up, square root of 9, square root of 29 equals x. And then last step, I can simplify. I know the square root of 9 is 3. So this is 3 square root of 29. Okay, and now I can leave it as is. Okay, remember we always need to look at that radical again. Square root of 29, are there any more perfect squares that go into it other than 1? Okay, well, other than 1, 4 doesn't go into it, 9 doesn't go into it, 25 doesn't go into it, and then everything else is too large. Okay, so we know we have simplified it as fully as we can. And as always, if we'd like to, we could plug this into our calculator and get the decimal, but this is why we practice simplifying radicals. We want to get in that habit. And so I'm just going to leave it like that. Okay, next one here, same idea. Use Pythagorean theorem to find x in this triangle. So again, good habit to get into is just to label your sides. So for instance, x here is one of the legs, so we could just label this as A, 9 would be our other leg, which is B, and then 11 would be our hypotenuse, which is C. Okay, so this is why I label them, because you don't want to get in the habit of just taking the two numbers that you're given and putting them in for A and B, because sometimes you're going to be given the hypotenuse instead. Okay, now that we have these labeled, we can go ahead and label, or we can go ahead and plug them in. So A squared, or in other words, x squared, plus 9 squared equals 11 squared here. Okay, and again, simplify like we have in the past. So x squared here, it's not going to change, plus 9 squared we know is 81, and then equals 121. Okay, and the good news here that I forgot to mention with A and B is even if we switch those around for x and 9, it doesn't really matter as long as we understand what the hypotenuse is. Okay, if you mix up which one's the shortest leg and which one's the longest leg, it's not that big of a deal. Okay, continue to solve here. We want to get x by itself, so we want to subtract 81 from both sides. When I do that here, these cancel. I'm left with x squared equals 121 minus 81, which is 40. And then we know the last step, we don't want to leave it here. We want to take the square root of both sides to get rid of that squared term. So I end up with x equals the square root of 40. Okay, and like I mentioned, if it comes out to be a whole number, then we could just write what that whole number is. But since we don't have that whole number, we need to break up and simplify this radical. And just like we saw before, there is a way to break this up. If I'm thinking of perfect squares that can go into 40, okay, that is, those factors would be 4 and 10, since 4 is a perfect square. So x equals the same thing as square root of 4 times the square root of 10. And like we've mentioned, I know what the square root of 4 is, so I can go ahead and simplify this. The square root of 4 is just 2. And then square root of 10 here. And again, need to double check. Can I simplify the square root of 10 anymore? I cannot, so I'm just going to leave it there. Okay, so these would be my two answers that I'm looking for, using what we talked about with simplifying radicals. Okay, another way that we can use the Pythagorean theorem that we have not seen before is being able to use what we call the converse of the Pythagorean theorem. Okay, the converse of the Pythagorean theorem. Okay, and remember we said the converse is just when I take an if-then statement and swap it around. So our original statement, or the Pythagorean theorem, says if this is a right triangle, then I can use this theorem, a squared plus b squared equals c squared. The converse of this is going to say if a squared plus b squared equals c squared, or I'm sorry, let me write this a different way. We're going to say if 3 side lengths in a triangle, try to be more specific or particular about it. If 3 side lengths in a triangle, and we'll just say, we'll call them A, B, and C. If those 3 satisfy this theorem, a squared plus b squared equals c squared, then what I can say is then the triangle is a right triangle. It is a right triangle. So last time we said, here's a right triangle, now I have this theorem. In this case, we're saying, let's assume that we don't know it's a right triangle. If I give you the side lengths, if this satisfies the Pythagorean theorem, then it has to be a right triangle. Okay, it works both ways, essentially. So our work is pretty much the same. The only difference is our end goal is we're basically proving that something is a right triangle as opposed to finding a different side length here. Okay, so I'll show this here in example 2. So example 2, again, you sketch this triangle here. And let's say we're given the side lengths 24, 32, and 40. Okay, notice in this case it looks like a right triangle, but we don't have that little box in the corner to tell us that that is a right angle. So what we're going to do here is we're going to use that converse theorem to prove that this is a right triangle. So if this was a right triangle, this would be our shortest leg, this would be our longest leg, and then this would be our hypotenuse. So I'm going to go ahead and plug these into the Pythagorean theorem and see if they come out to be the same. So we go here, we can go 24 squared plus 32 squared equals 40 squared. Okay, and if this comes out to give us a true statement, then it is a right angle. And there are going to be times when it doesn't work out, in which case we'll talk about what that means about those triangles here. Okay, so again, we can just plug these in here. There is a way to use Pythagorean triples with this, but for the sake of this problem, we'll just use our calculators here. So we have 24 squared, that's going to be 576. 32 squared, go ahead and type this in, that's going to be 1024. And then equals 40 squared, that one we can try to do in our heads. 40 times 40 is 1,600. Okay, and now we just need to double check. Take our two like terms and add them together, 576 and 1,024. And when I do add those together, I do in fact get 1,600 or 1,600. Okay, so this does check out. So that means that this is a right triangle. I'm going to say yes, it is a right triangle. Okay, so Pythagorean theorem works both ways. Okay, if the sides satisfy the theorem, then it's a right triangle, and if it's a right triangle, the sides satisfy the theorem. Okay, like I mentioned, there's going to be some times where it does not come out to be the same, and that's where we come up with these last theorems here, which is what we call the Pythagorean inequality theorems. Okay, the Pythagorean inequality theorems say this. It says if a triangle has three side lengths if a triangle has three side lengths here, and again, we'll just say A, B, and C. And I'm going to write it this way. I'm going to say if it has these side lengths such that C squared is less than A squared plus B squared. Okay, if this comes out to be the case, then what I can say is I can say then the triangle is acute. Okay, so remember, we're not just saying that the two sides added together are greater than the third, but we're saying, in other words, them squared added together, if it's larger than the hypotenuse squared, then that's not going to be a right triangle, but it's going to be an acute triangle. So for example here, if we're just looking at different sides here, we have A, B, and C here. And this would not be a right triangle. This would end up being acute if it satisfies that theorem. Okay? All right, and then one other thing that we have here, let's say it's a different situation. So they're not equal to each other and C squared is not less than. Let's switch it around and let's say it's more than. So I'm going to say if a triangle has three sides, or has three, let's do it this way, we'll say three side lengths. Fix that last one there. Again, A, B, and C. Okay, and this time let's say such that C squared is larger than the 2 squared. So C squared is greater than A squared plus B squared. Okay, if this is the case, then the triangle is not going to be right, and the triangle is not going to be acute, which means the only thing left is the triangle has to be obtuse. This triangle is going to be obtuse here. Okay? All right, and again, a little example if you want to draw that to the side. Similar kind of triangle, except this time C is going to be a little bit larger. So we want that kind of larger than 90 degrees here. How about that? A, B, and C. Okay? This would be an example of an obtuse triangle, and I'll show you kind of how this works, and we'll plug these in and see what happens here. But this is the basic idea. If it comes out to be this, then it's going to be acute. If it comes out to be this, then it's going to be obtuse. Okay, so let's practice that a little bit and make sure we have that down. And then remember, if it's not less than, and if it's not greater than, if it's equal to, then we've already said what that case is. That's going to be a right triangle. Okay, so last one here. Let's say we're given the side lengths of a triangle, and we want to use these to identify the triangles, or in other words, name the triangles that we have. Okay, when we're looking at these and we're trying to figure out which side lengths I should choose to be A, B, and C, remember, C should always be the largest one, so really you can just go in order. The smallest side will always be A, Next greatest side will be B, and then the largest side you always want to make C. Okay, so let's plug these into the equation here, and let's see what we get. So I'm going to start off with a squared plus b squared over here. So let's write this out. A, we said it's going to be 7, plus b, we said it's going to be 14. So I have 7 squared plus 14 squared. So 7 squared we know is 49. And then 14 squared, that's not going to be double that, but we can just type that into our calculator if we don't know. That's going to be 196. Okay, and then last one here, add those two together, and I believe this comes out to be 245 when I add those together. Okay, so I've got this here. That's a squared plus b squared. Now I need to do the same thing with c squared. Okay, so c squared here, we know we can just plug that in. That's 16 squared. And this one I'm just going to type in my calculator because I'm not entirely sure what that's going to give me. Okay, 16 squared, and that's going to give me 256. 256. Okay, so between these two values here, which one is larger? Well, we see 256 is going to be larger here. So we can go back to those inequality theorems that we said. Okay, if c squared is larger, then it's going to be obtuse. So that's what I would say here. I'm going to say this is an obtuse triangle. Okay, so notice how I don't need a picture of the triangle or anything like that, and I don't actually need any of the angle measures. I can just use what I know about the side lengths to be able to tell you, no matter how you made that triangle, it's going to have to be obtuse. Okay, all right, and then last one here, let's say we have 5, 6, and 10. So we'll look at this here. We have 5 squared plus 6 squared, or let me write this out first. I'll say a squared, a, b, and c. A squared plus b squared over here, c squared over here, and then we'll see which one comes out to be larger. So right here, we have a squared, or in other words, 5 squared plus b squared, or 6 squared. Okay, when I simplify these, 5 squared is 25, 6 squared is 36. Okay, and then same thing over here, or sorry, I want to simplify this. Let me focus up here. 25 plus 36, that is going to give me 61, I believe. Okay, and now we do the same thing over here. We have c squared, or in other words 10 squared, and that's going to be 100. So again, what pattern do we see here? We see that 100 is going to be larger than 61. So what kind of triangle is this? Again, this is going to be an obtuse triangle. Okay, so we're just using those properties that we talked about. Obtuse triangle there. Okay, if c squared comes out to be larger, it's going to be obtuse. Okay, if it comes out to be less, then that will be acute. Okay, so this is the work that we need to be able to do for today. The assignment for today is 9.2, and that should be posted on the class website. Okay, and as always, if you guys have any questions, feel free to let me know. All right, thanks, guys.